So let's begin. So today we'll have about the spectral element method, or methods. So you've all been working on finite difference methods, where you have a regular grid, where each grid is regular. So this is a finite difference method because the difference is finite and it's constant between each of the cells. Spectral element method, that's a subset of a finite element method. So say you have the same kind of model, but you can cut the models, no, the elements as you see fit. If you have an area with a lot of, for instance, changes, then you can have a finer grid there and a coarser grid where there are less changes. So for instance, if you have an interface, you would maybe have more cells there or more points, more grids there, which you can have with the finite element method. So with the finite difference, then you have this set. So if you have lots of information up here and not so much information up here, then you need a fine grid and a fine all over. So you can do more stuff with a finite element method than with a finite difference. Problem though is actually creating this so-called mesh. That's a science in itself. To actually create a mesh that makes full use of the finite element. Finite element positives. And as you can see, I mean, the finite element, this is generalizable down to the finite difference one. Because, I mean, this is a special case of it. So, some advantages, it is usually more accurate. And it can deal with a lot of more different stuffs than just a finite difference. But the disadvantage is actually creating this grid, and it's also a bit more computationally intensive to do it. But once you've actually created the mesh and the nodes and everything, then it's better. But it takes a lot longer to actually get it to work. So you will be struggling with the finite difference method, so the regular sampling. That's what you've been doing on the project. And some of you have been struggling with this, so you could try with this instead. It's harder, and also keep track of like which node is adjacent to which other node. It's a mess. So, as an example, to actually use this, I will introduce the weak solution of the wave equation. I'll use a slightly different wave equation that you have in the project, and I'll explain why. 1D scalar wave equation. So, of density as of position, then displacement of t minus dx ones u of x dx of x of t equals some kind of driving force of x. Like so. Did you see the difference from this equation and the one you're solving? They've kind of split out this differentiator here. But if we have that dx mu, which is the kind of the elastic parameter of it, or how compliant it is to changes, if this is lower or much lower than dx u, so mu and u, then we will have that dx u dx u approximately equal to mu dx squared u. And then you should get back to your other equation I've provided for the project. This is basically say that the model parameters change slowly compared to the displacement. So this would hold true for most cases, well, except in interfaces. So if you have a boundary, so you actually do have a boundary in your model, then this xu is not small compared to the displacement. So this is well, it has more physics going on in it. It's also a bit harder to implement. That's why I opted for, well, this approximation. But that was kind of like a side note. Okay, so this is a 1D equation. We will say that x, right here now, x goes from 0 to L, so just along a segment or a line, and the time goes from 0 to capital T. Then we'll use the Neumann boundary conditions, which is that there should be no displacement ends x equals 0 is the same as dx t. The end is 0. And also the initial conditions, it's going to start quiet. Basically, u d 0 equals 0, 1 dot t 0 equals 0 as initial conditions. Okay, so this is the strong formulation of the wave equation. But we will be using a weak formulation, which is we will basically introduce an average test function. I call it W, and that has compact support on this segment here. So what is compact support? Just a fancy term for mathematical consistency. So. Yeah, let's just do the support first. So this is a strong formulation. I will try to get the weak formulation, but in order to get the weak formulation, I need to multiply this equation with a test function that has so-called compact support on this segment. So the support from kind of region X to R. So the support of this function f all elements x in capital X such f of x 0. Okay. And that it has a compact support means that these x's are a compact subset of. Does that make sense? Okay. So, more definitions. This is just to make sure that all the math plays nice later. So first, just words. So a compact subset. well, a generalization of a space being closed. What is a closed space? What do you think a closed space is? So here we're working in 1D. So a closed space here is, for instance, this here, 1, 2. That's a closed subset. So if you have many of these that are closed, then you can get a support for this. Okay. And an open set, 1, 2, that's not closed because it's an open set. That's no good. Also, just numbers will be closed. 1, 5, 6. Those are closed sets. But in a more general sense, if you have 2 dimensions, then you would have, for instance, a square with including the border. That's a closed subset of 2D space. 3D space, cubes, sponges. Well, sponge is something math, but say this. If you have enough of these, you can stack them and you can actually fill this room. It's a closed. You can have a support of remotes. Okay. So this function, W, is a so-called closed, a compact port on our interval. From L to R. Okay, so this is my test function. And it plays nice. Okay, so what I'm going to do now is just basically multiply my 1D scalar wave equation with this test function. And also integrate over the elements. Or integrating over space. And then I get the weak formulation. Internet, we do X row, oops, row, X, E, W, X, dx, U, dx, U, dx equals X dx over some kind of G. The G here is just an element of this interval. And also, I've dropped all of the dependencies here. So rho, of course, is a function of space, so x. Same with this, is a function of space and time, the same as over there. This is my weak formulation. And if you compare it with the, I guess we can call it the strong formulation of the wave equation, is this. It kind of looks more scary because you have more variables in it, and also you have these integrals, but that clears up in a while. We can actually do some of the, or integrate away some of these parts. So do you all remember integration by parts? Like calculus 1? So that says that the FG x fundamental theorem. No. So x dx, where the derivative of capital F is small f, and the derivative of capital G is small g. That's integration by parts. We can actually apply this to our weak formulation, make it easier. Okay, so what happens if you apply this to the weak formulation? We should get W O dx. Okay, so nothing there. Plus dx W mu dx x minus this part W mu dx u. So we integrate this bit from x0 to L, and then we have driving force as well, dx. Okay, but we can do something easier here. So what is, where are we now? Here. Okay, so take a look at this and look at the boundary conditions. Okay, so what is dxu at x equals 0? 0. Okay, and dx of u at x equals L, that is also 0. This just disappears. This means that we have already taken care of the boundary conditions. You get them for free. Vector element method. This works. This bit zero. And we've taken care of our boundary conditions. For free, almost. Like that. So then, weak formulation of the up and up with P W O U double dot dx plus roll dx W mu dx w dx GW which is the weak or sometimes called the variational form of the wave equation. You see, I've switched the position of these because this is just a multiplication. So I've just switched those. Okay, and the initial conditions for this will be D rho W mu 0 dx rho u dot t 0 x equals 0. And a solution that will satisfy this is called, well, a weak solution. Well, keep with the theme. Okay, so we've done some mathematical gymnastics. So what are the advantages of these? I mentioned one of them, and that is the boundary conditions are automatically included here, which is not the case in finite difference. As you see, you get reflections from the boundaries in your projects. Using this equation, you won't. It's just baked into the weak formulation of the wave equation. And also, the solution may be less so-called regular than the strong solution. So the weak solution need not be first-order differentiable. You can have sudden spikes in your solution, and it will still make sense. And in some cases, the weak solution is the only real-world alternative, because you can't find differences. Okay, but we're only, well, not even halfway there. We need to do something with this. So what we're going to do now is we're going to try to solve this using basis functions, which you can reuse over and over again. And before we do this, I'll introduce something called Larkin Projection. So don't mind the fancy names. Just some kind of smart guy who did something first and got his name on it. It's basically an approximation. Projection. And I think you've done a similar trick in calculus, only not by this name. Okay, so we're going to approximate the so u of x of t, so this is the exact solution by a finite superposition, again, fancy word, just basically means adding. Of n basis functions. I. And these will only depend on space and not time. Such that the approximation, so let's see, bar is the sum I equal 1 n I time times the I x should be approximately equal exact solution. So you're splitting the function into two different functions. One function that is only temporal and one function that is only spatial. These psi i's, they are going to be basis functions. So when you have basis functions, it's easier to manipulate them later on. And then how good is this approximation? That depends on all of the parameters. So it depends on which, so we have to pick these, we have to pick some kind of basis function. We have done this before, it could be polynomials. And also how many of them we have, source we have, which densities we have, and which elastic parameter u we got. So it all depends. But I mean, it's easy if you have some kind of general sense of how to do it. You can just use more and more and more basis functions, and it shouldn't really complicate your problem. It's only going to be more computationally expensive. Okay, but the next, we require that this approximation actually solves our 1D scalar wave equation. Okay, so we basically just do the approximation and then we inserted our 1D scalar wave equation. And this should hold for each and every basis function Ci. So the next one we have G rho I bar dx plus dx Ci bar x dx. And again, the initial conditions should be E O I U 0 rho Ci dot T0 dx 0 for all I for all of the basis functions. This should hold true. This is what is this? This? So Galactic Projection, that is basically an approximation. So we approximate our function, which is a function of, well, this is the exact solution, u of x of t. We approximate it with basis functions or spatial basis functions c and some kind of temporal we call them, well, coefficients that would evolve in time. It's just basically splitting it. So we can do space using these and then these for all. So it's just a trick. Do it. Basis functions, it could be polynomials. It's something that you use to span a space. How more to say it? So say polynomial space. 1, x squared, x or 3, those are kind of basis functions in that space. Build it up. So since we are only working in 1D now, it's kind of easier to imagine. So one basis function would just be this. Another basis function, use colors. Another basis function would just be a constant, like so. Or this. More of them. So those are basis functions. This is basically the functions we will use also later. So either constants, slowly varying, or more or less. Well, that's, yeah, you got a point. So a superposition of these. So you're basically adding them in such a way that you can get whatever function you want. This is similar to what we did with polynomial interpolation. There we also had these kind of basis functions, which you can use to approximate a whichever function you want. So again, we are using interpolation here, or the approximation. Okay, so using this approximation and the weak formulation, we would get, so we have to sum over all of the basis functions. So from I equals 1 to n, this is the amount of basis functions. We will also have more functions later, which I come back to. It's going to look of t. Now we can actually put this outside of the integral. What we're after, e rho c. Let's see, I missed the point. Yeah, no. Yes. Now we have two of them. MC. So I'm also going to say that the test functions I use, the W's, so these, that would also be a basis function. Makes stuff easier. Because these are, the test functions, those are arbitrary. And if I pick them to be a basis function, if the basis function has certain properties, you will see that it's going to be easier in the end. So this I, this is the basis function, this is the test function. J's. No. I, C, and everything inside of the integrals are dependent on space. Oh. x j c dx c I dx. J f dx over g. And then for all test functions, Cj. So do you see everything that's going on here now? I've just renamed my test functions from W to Cj. That should be possible. As long as these test functions satisfy whatever it is, then it should work. And also I've done the approximation that u of x t approximately equal to I1 I x I of t, such that I can actually put the ui's outside the integral. Hmm? Oh yes, there should. Yeah, sorry, there should be a bracket here as well. My bad. I forgot to close it. Yeah, but there's going to be more sums later, I'm afraid. So I've just picked these, so they are the same functions. Okay? I should be allowed to do this. Does that make sense? Maybe? Okay. We can now write this as a matrix equation, a so-called algebra differential equation. So we have the equal with the drill strings, m times u t plus k u of t f e, well, f vector, like so. Only thing I have to do now is to find the m and the k matrices. Well, also a source term. So now if I have that the element of the matrix, so m, I, j, the so-called mass matrix, g, rho, j, c, I, dx, and the stiffness matrix, okay, ij equals g mu dx j I dx, and the source terms j cj So then you see we've been able to kind of separate out time. I can name them also. And what should we call the last one? Force turn. So. This kind of looks like a spring, which is why you have the name stiffness. So that's kind of the stiffness of the model matrix. But it's not a matrix model. Okay, so before doing how we can decompose this, I kind of showed it already though, but how we can decompose the model. This is just a string though, but I will also do it in 2D. But I think that's a good time to have a 15-minute break, unless there are questions.